Hey everyone, today we're going to look at this interesting circuit diagram where we have to find the equivalent resistance of the circuit or net resistance, and we also have to find the ratio of the potential between point X and Y to that of between point Y and Z. Before we proceed any further, let's remind ourselves what are the resistors connected in parallel and in series in a circuit, right? So this circuit shows R1 and R2 being connected in parallel to each other, right? So in the case of parallel resistances, the equivalent resistance is going to be given by this formula. It's where the reciprocal of the equivalent resistance is equals to the sum of reciprocals of individual resistances, or it works out to be this for the case of two resistors. The net current is going to be sum of the current that's going through the first and the second resistor, which kind of makes sense. Your current comes here, splits into two, and then at this point it combines back and goes into battery. And the potential drop across the first and the second resistor is going to be same as the potential drop across a battery. In the case of in series, your equivalent resistance is just the sum of the individual resistances, and the current going through the first one and the second one is going to be actually the same as the total current, so I equals to I1 and I2, right? Because the same current has to pass through this to complete this loop. And the potential drop across this one and this one adds up to potential drop across the battery. So now if you look at our circuit, maybe except this two, I don't see many things being connected in parallel or in series, right? This one looks like they are in series. So this circuit looks a bit scary compared to what we are used to, right? This is what we are used to. So what are we gonna do? Well, what we're gonna do is we're gonna start to identify which ones are in parallel and which ones are in series. So this is our circuit, just magnified version. So what I'm gonna first do, I'm gonna label the plus side of the battery with, say, red color and the blue color. And I immediately notice that this junction, there is no resistor, right? So potential drop, potential at this point is gonna be exactly the same as the potential at the battery. But here I already have resistors, so current has to go and then potential is gonna drop. So it's not gonna work at any of these points. But in this point Z, potential is the same as the potential negative electrode of the battery, and potential is the same at this point as well, because there is no resistors in here, right? So we identified where the potentials are the same. So here is the same, and here is the same, okay? That means that potential of this one end of this battery and this one of the end of this resistor and this resistor have the same connection. Similarly, for this 6R resistor, and R, they also share same connection. Now let's look at the Y point. Okay, so Y point is just like a kind of orphan here. So Y is connected to 6R, 4R, and 6R. So now we know which connections share the same points. Well, let's redraw this circuit. So the equivalent to this circuit is going to be this one. Why? Because for 4 and 3 R's, I have to share the same point, which I do in this diagram. And then after 3 comes my R here, and this is blue. It should be connected to one of the 6R and to the second of 6Rs, right? And the other end of the 6R resistors have to be connected to 4R resistor. And that circuit fulfills this criteria. Now my circuit looks immensely simplified. So I can go ahead and start calculating things here. Well, okay, now we have to work with this simple circuit. So right away we spot that 6R and 6R are parallel to each other. So equivalent resistance of these two resistors is just 6R times 6R divided by 6R plus 6R, which works out to be 3R. Now this 3R is in series with this 4R. So this resistance is actually 4R plus this one, 3R, which is 7R. Okay? What about this two? They are in series, right? It's even obvious from this figure. So if you have 3R and R, if they are in series, it's just sum, so you have a 4R here. So now you have 4R in parallel with 7R. So that would be just 4R times 7R divided by 4R plus 7R is your equivalent resistance, and which works out to be 28R divided by 11. And this is the answer for the first part of the question. Now, what are we going to do about the second part, where we have to calculate the ratio of the voltages between this red and green and blue points? Well, we know that red point corresponds to the beginning of 4R, and green point corresponds to point where 4R meets with 6R, and the blue point corresponds where two 6Rs meet, right? And we know that the resistance of this point, of this region, is just 3R, and this is 4R. So voltage across X and Y is just whatever current flows through here times the resistance of this part, right? So it's I times 4R. This is just simple Ohm's law. What about between Y and Z? So same current comes and travels through this equivalent circuit, which is 3R now. I times 3R. And we take the ratio, it works out to be 4/3. I hope this is clear to everyone. And thank you.